Hi, I'm Chris Curzon, and this is my small presentation on programming paradigms and our approaches to problem solving. The first domain we will talk about is the imperative domain. Imperative is a step-by-step carrying out of instructions to reach the desired outcome. This is perhaps the most intuitive way to program. When you break down a problem into smaller steps, you are specifying what to do at each stage, saying which path to take under which conditions. It is also characterized by tracking of state via variables and the modification of these states to change how the program and other functions behave. It is difficult, therefore, to predict what a particular function will produce because its initial state matters. To show an example of this, this is an example that depends on a variable called user logged in, a Boolean variable, to see what the state of the current program is, and depending on that state is going to our function display dashboard will return a different object based on this variable. It's therefore difficult to say in advance what this function will produce because it depends on a variable outside of its own scope, and the state of that variable will produce different results for the function. It is, however, a step-based program because based on the step where we are at, we can reuse this function to produce different results. The second domain we will talk about is the declarative domain. The declarative domain defines the rules of a game. It is a more mathematical approach to programming where consistent rules define the relationships between concepts. I really like this quote from Wikipedia, where it says, in computer science, declarative programming is a programming paradigm that expresses the logic of a computation without having to describe its control flow. The most used subdomain of declarative is the functional domain, where a functional programming, every function only operates within its own scope. It never modifies the state of a program or mutates any objects outside of itself. And it's called a pure function when it's deterministic. It always returns the same output with the same input parameters. And using pure functions minimizes the complexity of programs because it's easier to predict what it will do and what it will produce. It's consistent in the fact that we can always be sure that it's going to produce the same output with the same inputs. I have an example here of a purely functional function called the Fibonacci function, which returns the nth Fibonacci number. And a pure function purist will also say that a true function relies on recursion to accomplish its task, as is demonstrated in this example. So this function will call itself if the argument isn't one of its base cases. So if you know the definition of the Fibonacci sequence, the 0th or the first Fibonacci number is 0, the second one is 1, and then any Fibonacci number is always the sum of the two preceding Fibonacci numbers. So this expression quite succinctly captures the definition of the Fibonacci number and also recursively calls itself in order to reach that. So if whenever we've got 0 or less than 0, just to make sure if we get negative inputs, we get 0 because there's no such thing as a negative Fibonacci number. Or if we have 1, we return 1. But otherwise, we look for the numbers prior to that and add them together. But while recursive functions are succinct and mathematically correct, they're often not very computationally efficient because they tend to grow the call stack exponentially, like my poorly implemented example here. But oftentimes, specialist hardware and clever implementations can circumvent this issue. And we also have to talk about object-oriented programming for a little bit. Object-oriented programming is mostly considered an imperative design, but this does not strictly have to be true. One can use a declarative approach and object-oriented programming. But the reason why it's mostly used for imperative designs is because object-oriented programming is very good at tracking state, and it's very good at modeling systems that aren't strictly mathematical and that closely resembles real-world scenarios or real-world objects to track that state of the real world, which we then model inside of the computer and then carry out functions based on that. But a declarative approach in using object-oriented programming would be something akin to having all classes be only singletons, because there's no need for various instances if you're not tracking state. All your methods will have to be static and all your properties read-only. I'd also quickly like to talk about idempotency. Idempotency is a concept whereby the modifications that a function produce is singular or unpredictable. What this means is that when a function is called and it changes something, whether this change will be different if the function is called a second time or a third time. So an idempotent function means that if you call it once, it will change something, and if you call it a second time, it won't change it past what it's changed the first time. A non-idempotent function will be calling it over and over and every time the state changes. To show you an example of this, in the imperative domain, a non-idempotent function would be something like toggling the class list of an element. The toggling will change the state of the class list at each function call, so either to have it or not to have it. Therefore, every time we call it, we'll have a different state, and we can only predict what the final state will be if we know the initial state as well as the number of times it was called, in this case an odd or an even number of times. An idempotent function, on the other hand, is something like adding a class to a class list. Whether we call this once or many times, it doesn't matter. The class will only be added once, and therefore we can also predict what the outcome will be when we call this function. Inside the declarative domain of more mathematically succinct functions, something like calling exponent many times on itself is going to produce different results based on the number of times that we've called it. But something like calling the absolute on an integer will be the same whether we call it once or many times. We will always get the same output. Then what about JavaScript? So JavaScript has features that allows us to write both declarative and imperative approaches. Things like regex, which can be written as literals in JavaScript, are declarative in nature because we specify what we're looking for, not how to look for it. Any function that depends on the state of another modifiable variable is imperative. And we can argue that most things in JavaScript will be imperative as we're changing the state, which mostly has to do with user interfaces for JavaScript. But then I want to talk quickly about software in general and the argumentation of what is better and what it really is. And one could say that arguably all software is imperative at its lowest level. Assembly language, the lowest human readable language that we can write, can only be a sequence of step-by-step instructions and therefore is imperative in its nature. And this is true for even functional languages like Haskell can be compiled down to assembly language, which we would call a purely functional language. But that doesn't have to stay that way, or we don't have to necessarily say that that's true in all cases. I'd say it depends on our level of analysis. Encapsulation hides away many of our implementation details, and this is really what defines a declarative or an imperative approach. For example, inside of a function, we may define logical steps to obtain a result, modify internal variables inside the scope of the function alone. And in this way, you can call it imperative because it's a step-by-step way of solving a problem. But from outside of the function, if we don't modify a state from outside of this function, and we can predict its return values based on its inputs, it is declarative because it's easy to predict what's going to come out of it whenever we give inputs, and it's not dependent on the state of anything else outside of it. So it depends on our point of view on whether we say something is declarative or imperative, and at what level of analysis we are working. And in keeping with this, let's talk about our project. Looking at the projects we've been asked to analyze to determine whether they're declarative or imperative in nature, I'll start with example 2 on the right-hand side. On first glance, for me, it seemed almost like it was declarative, based on its definitions and the uses of switch cases. But upon closer inspection, I had to settle with the fact that this is an imperative function through and through. The first hint to this decision is the fact that this function doesn't return anything in and of itself. And it uses console log to output its status at every step, which is another hint to the fact that it's imperative. It operates by steps and side effects. The side effect being console log and the steps being a loop determining then what to do at every stage. So function 2 or example 2 is definitely an imperative function. Example 1 is a little bit more complicated to analyze, and the reason for that being is that this function isn't complete. It's ambiguous in its statement because it seems to imply that it will always cook a steak regardless of its inputs, which looking at its inputs, that's what you want it to do. You give it a certain size steak and a certain level of doneness, and then you want the steak to be cooked. But the reason why I still think this function is ambiguous is the fact that it doesn't really have any meaningful return values and that it has an infinite loop set up. So this function will never actually return anything. It will keep on running forever, blocking the main loop if it's run in the main loop, or if it's run in an asynchronous thread, that thread will just keep on running forever and not return anything at all. But we can actually make this function declarative by giving it a return value of the cooking time that will be needed to cook that size steak to its certain doneness. If that functionality is implemented into this function, it will be a declarative function, regardless of the inside of how this function works. Because looking from the outside, we will always get the same return value based on the inputs that we give it. And it doesn't operate by any side effect. It doesn't modify anything outside of itself. It's got a perfect local scope, takes your inputs, doesn't modify the inputs, and gives you an output. So example 1 is very, very close to being declarative, but at the moment it's an unfinished function with no meaningful value whatsoever. It doesn't do anything because it's just an infinite loop. So that's my analysis of the project examples. Thank you very much for joining me for my presentation, and hopefully I'll get better at these, and I'll see you at the next one. Bye.